Okay, hi guys, welcome back. I'm recording another data analysis video here. In the last few videos, I've been demonstrating how to conduct one-way ANOVA tests. So both independent groups and repeated measures. Something I have not really covered though was tests of assumptions for ANOVA. So these are things you want to check before running an analysis of variance and ANOVA statistical model to make sure that your data is appropriate for fitting such a model. So standard ANOVA tests assume that the data being compared is suitable for a parametric statistical test. And it's often worth checking that the data meets these assumptions before running an ANOVA, as unsuitable data can lead to erroneous results and findings. So some common tests of assumptions for ANOVA that are worth conducting and checking before you actually fit the model are for between subjects designs, for independent groups designs, are tests of homogeneity of variance, or often referred to as equality of error variances or equal variances. So these tests, or this type of test, a test of homogeneity of variance, is to check the assumption that the different groups that are being compared have roughly the same or equal variances around their group means. And a frequently used test for this is known as the Levene's test. Okay, so I'll demonstrate that in this particular video for an independent groups design. If you have a within subjects or repeated measures design, you can also conduct what's known as a test of sphericity. And this is kind of a repeated measures equivalent of the independent group's test for homogeneity of variance. So sphericity can be defined as the assumption that the variance of differences between scores across groups for data taken from the same participants are equal. So a commonly used test of sphericity is in repeat measures designs is the Mauchly's test of sphericity, and I'll demonstrate that as well. A third assumption that is worth checking is the test of is testing for normality. So a normality test assesses the extent to which the distribution of scores for a variable differ from a normal distribution. So normally distributed data is an assumption for all parametric statistical tests, and that's necessary for both independent and repeated measures ANOVA designs. And a commonly used test of normality is the Shapiro-Wilk test. And when you conduct a Shapiro-Wilk test, if you get a significant test result, it indicates that the data deviates significantly from a normal distribution. And that's the same with these other tests, these tests of assumptions. So if you get a significant test, Levene's test for homogeneity, it means that the variance around the group means differs, and a significant Mauchly's test, the same sort of thing. It means we're kind of, if we get a significant Mauchly's test, a p-value less than 0.05, say it means we've violated the assumption of sphericity, and we can't assume that the kind of error variances are equal. The differences between scores across the groups are roughly equal. Okay, so that's a kind of important thing to make to understand is normally when we're conducting these sort of statistical tests, if we get a statistically significant result, we've found some hypothesis test, we've found a difference. It's the same thing here, but what it's telling us is that we violated some assumptions that we need to meet. So our data is probably not appropriate for parametric statistical tests. So all of these above tests, the three that I've just mentioned, have limitations, and there are lots of debates about how useful they are, what their value is. So for example, statistical tests that assess normality and equal variances can be sensitive to differences in sample sizes. So if you've got a very large sample size, what you might find is it's possible to detect quite small differences in terms of variances between groups as being statistically significant, and those differences might not have actually been problematic or invalidated the results of an ANOVA model. So it's worth keeping in mind that these kind of tests are convenient. They're useful in some ways for just kind of checking to see if we've met these assumptions, but there are limitations to them, and some people, many people don't think they're actually worth doing, and it's probably better to use just more robust types of analysis. Okay, but I'll demonstrate them here so um, people are aware of them and are able to use them if they choose to when conducting these types of frequentist hypothesis tests. So what I'll demonstrate in this notebook is how to conduct Levene's test for homogeneity of variance, Mauchly's test of sphericity, and the Shapiro-Wilk test of normality. And I'll use the scipy software library, and I'll also use Pingouin, which is another software library available in Python for conducting different types of statistical analysis. It's a really good library. You can run lots of quite good models in it. So let's start with Levene's test. So homogeneity of variance. What I'm going to do here is I'm going to conduct a Levene's test using the Levene method from the scipy .stats software library. What this does is allows me to specify that the mean is used as a measure of center for the test. If we use the Pingouin package, so the equivalent, you can do Levene's test in Pingouin or in scipy. If you use the Pingouin equivalent to run the Levene's test, by default it uses the median and is thereby conducting a slightly different test called the Brown-Forsyth test. In this case, we just want to use the mean for a standard Levene's test, so I'll just use the scipy.stats method for this. Okay, so let's get started and import some software libraries that we're going to need to conduct this analysis. I'm going to import pandas because we're going to import some data, and I'm going to import scipy.stats, or from scipy.stats I'm going to import Levene, the Levene method. Okay, so I'm going to import a data set that I've got saved on my laptop to work with. So I'm going to save it as df_ig, so independent groups data frame, and it's an independent groups design. And I'm going to use the pandas pd.read_csv method, and the data set is called puppies.csv. It's a comma separated value file on my laptop about data around something called puppy therapy. So it's a data set and an example that comes from the Andy Field statistics textbook. I think it's an introduction to statistics using IBM SPSS. Okay, I'm obviously using it in Python here as a CSV file, but that's the kind of source of the data. It's possibly, I imagine it's a made-up example, but I think the idea here is that people were allowed to spend time with puppies, either a small amount, a medium amount, a lot, low, medium, high. So they're the grouping variables, and then they look to see how happy they were. Okay, so let's import that data set. You can see the variables. We've got a person ID. We've only got 15 participants. That's the whole data frame. We've got 3 groups under dose, 1, 2, and 3, low, medium, and high. How much time? These kind of just a category of whether they spent a small amount, a medium amount, or high amount of time with a puppy, stroking a puppy, maybe something like that. And then some kind of scale of happiness from maybe measured from 1 to 10. All right, so we've only got 15 participants. We've got a categorical variable of dose, which is currently shown as numerical values 1, 2, and 3. And these 3 values correspond to categories low, medium, high. So the first thing I'm going to do is manipulate this data a little bit to make it, to get it in the sort of format that I'd like it in, and add some category names that are more meaningful. So I'm going to use the series.map function from pandas to add labels to the dose variables. So what I'm doing here is I'm creating a couple of lists, A and B. List A just contains numbers 1, 2, and 3, which correspond to 1, 2, and 3 for our dose variable, and object B is going to be low, medium, and high. And I'm adding a new variable called dose_cat for dose categorical to our data frame object df_ig. and I'm setting that equal to dose underscore independent IG, our data frame object variable dose, and I'm kind of using the dot map method to zip together these two lists I've created, A and B. So all I'm doing here is, and you'll be able to see that when I run this, what I've done is created a list of our category numbers, category labels we'd like them to be. I've used dot map to match them up, and created a new variable that's appended to the end of the data frame. As I've said in previous videos, when I do things like that, I kind of like to leave the original variable in place and append a new one. If I'd have specified, as I've got dose here, if I'd have just specified dose here, it would have just relabeled them on the original column. But there we go. So there's a couple of other things I want to do. I want to compare variance around the mean happiness score for each of the groups. So to do this, I'm going to create 3 new variable objects that can then be passed to the scipy Levene method for comparison. So I'm basically creating a new object called cat, which consists of the dose category, variable low, medium, and high. And I'm going to create another object called scale, which is our scale kind of dependent variable, happiness. So we're looking at an IV of dose and a DV of happiness. So I'm creating 2 new objects that basically just contain the data from those 2 variables. And then I'm going to create 3 Boolean objects that splits category up by the level of condition. So we've got cat here, which is just this variable. And then I'm going to create category cat1, which just contains the observations in the low group, cat2, just the observations in the medium group, cat3, just the observations in the high group. So what you can see here, I'm saying cat1 equals, so I'm creating a new object, and it equals all the observations in our cat object that are exactly equal to low. Likewise for cat2, etc. Okay, so finally what I'm going to do is create a list of each happiness score broken down by category. Let me run these things because I'm skipping over them, so I'll forget to run the cells if I don't do them now. Run those 2. We're up to here. So you can see now we're getting sort of slightly more granular. What I'm doing here is now we've got these cat 1, 2, and 3. We've got our levels broken down, and then we're gonna sort of create these new objects which map our scale object, which is our happiness score for each group. So all we're doing really is extracting each of the groups and then extracting the happiness scores for each of the groups, essentially, by doing this. And I'm saving them as 3 new objects: categorical happiness low, categorical happiness medium, categorical happiness high. Okay, so 3 new objects now exist, essentially, which and you can't see them, they're running in the background, which we can manipulate. And all I'm going to do is pass these 3 objects as our 3 groups to compare to the Levene's method from scipy. So I'm running Levene's test here by passing those 3 grouped happiness scores objects, and I'm going to specify that we want the measure of center be the mean for each group. Okay, to do that, all I'm doing is I'm calling Levene, the Levene method. I don't need to specify stats.levene because we kind of specifically imported it as from stats, so we can just call it. If I'd just done here from scipy import stats, what we'd have to do here is we'd have to do stats.levene, something like that. Okay, so let me run that. So we've got our 3, you can see there we've got Levene, we've got our first group, second group, third group, happiness scores for low, happiness scores for medium, happiness score for high, and we're saying use as the measure of center for Levene's test the mean of each group, and that's just passed as a string variable. So what you can see here, we've got for Levene's test, we've got a test statistic of 0.09 and a p-value of 0.91. Okay, so that's a non-significant Levene's test. What that's telling us is that that we're probably safe to assume equal variances between these three groups in terms of variability around the group mean. Okay, so that's kind of a good thing if we wanted to then conduct an ANOVA on this data. When you report Levene's test, it essentially conducts an ANOVA, and we'd report it as like an F value, as you would an ANOVA. But there's obviously, it only gives you here the test statistic and the p-value. But to report that formally, there's additional info we need, so we need the degrees of freedom. And when you can't use the scipy Levene's method, it doesn't give you that. So what we've got is a Levene statistic of f equals 0.09. You can see that there. An associated p-value of 0.91. So it's a non-significant Levene's test. The null hypothesis for Levene's test, as I said previously, is that the variances between the groups are equal, which is the assumption we're seeking to meet to be able to conduct an ANOVA test on the data. So here, as we've got a non-significant result, we can probably safely assume homogeneity variance for our data, and we're probably okay to run and interpret a standard ANOVA test of whatever our research hypothesis was. Levene's test here hasn't given us the degrees of freedom, so to formally report this, we want to also report those degrees of freedom, and what we'd have to do here is, I'll demonstrate how to do this, but we're going to have to calculate it manually, which is a little bit laborious. So to calculate what we need are the between groups degrees of freedom and the within or the area degrees of freedom, essentially. So we report those in parentheses after the F for our F statistic. The way we calculate the between degrees of freedom is k minus 1, where k is the number of categories or groups and n is the total number of scores per participant. So k for the between groups degrees of freedom, it's k minus 1, k is the number of categories. For the within, it's n minus k, and n is the total number of scores. So we take the total number of observations participants and we subtract the number of scores. So I'll demonstrate that. I'll show what that means with this particular data set below. And we can also calculate the total degrees of freedom. That's just n minus 1 in this case. The two we need, though, are the between and the within to report. So for this particular data set, we've only got 15 participants and 3 groups. And so the between is k is our number of groups, total number of groups, that's 3 minus 1, that gives us a 2. The within, we've got 15 n minus k, so we've got 15 participants, n of 15, minus k, the number of groups, 3. So 15 minus 3 is 12. And obviously for the total degrees of freedom, we've got 15 participants minus 1, that's 14. So if we were needed to formally report this Levene's test, which often you would before reporting the results of an ANOVA, you'd kind of need to include those between and within degrees of freedom. So it would look something like here. You'd have an F, open parentheses, 2, 12. So that's the between, within degrees of freedom. Close parentheses, and that equals, and then whatever the F statistic was. Remember, in this case, it was 0.09 if we round it to 2 places. And then P is equal to 0.91 in this case if we round that to 2 places. Yeah. Okay, so a little bit of a laborious way to do that, to work out the degrees of freedom, but that's how you can do it. But we can also create formulas to work those out for us. This was easy because we've only got 15 participants, we've only got 3 groups. But if you had a large data set with a large number of groups or being compared or something like that, then we'd probably it might be nice to kind of use a formula that helps us work that out. So that's all I'm doing here is I'm gonna get Python to work out k for me and work out n for me. Okay, so what I'm doing is k is equal to the length of remember k is our number of categories. Let's scroll back up there. K is our number of categories. So to work out the number of categories, we're just going to ask how many unique categories do we have, and passing in our cat object we created, and that's going to be 3. So, and how I'm using the len function. So length k is equal to the length of the number of unique categories. That's all that first line of code there says. Okay, n is to get n, I'm using kind of a crosstab, pandas crosstab, and I'm specifying category as one of the variables, scale is the other, and I'm using this double dot sum notation that I've presented in different videos. So what you'll see here is if I run this, it'll tell us exactly what k is and exactly what n is. It was easy for us to do in this case, but it might not always be, and you can obtain it by like asking for the dataset info or something like that. But this is kind of just a quick way to sort of code it, so you can work out number of participants and number of groups. Right. So with these values k and n, 3 and 15, we can then work out the degrees of freedom using the above formulas. So I'm just degrees of freedom between is equal to k minus 1. We know what k is here. We've worked it out as 3. Degree of freedom within is n minus k. So we know what n is, 15. We know what k is 3. And we've also got the total degrees of freedom, n minus 1 there. And all I'm doing here is separate by commas. I'm just going to print out what those values are. And you can see now, so we've worked out k and n, and we've also got Python to calculate the degrees of freedom between, within, and total for us. Okay, so that was the scipy Levene's test for homogeneous variance when you have an independent groups design. And remember, we used the scipy version because it's if we use, there is a Levene's test in Pingouin, but it uses the median as default, and by doing it's conducting a Brown-Forsyth test, which is slightly different. So we just did a bog standard Levene's test here. Okay, so a couple more. I said I'd demonstrate Mauchly's test of sphericity as well. So remember, this is a repeated measures equivalent of a Levene's test. It looks to see if the variance of different scores taken from the same participants between all pairs of groups in the categorical variable are equal. So I'm going to demonstrate Mauchly's test using the sphericity method from the Pingouin package. I really like Pingouin. So I'm going to import Pingouin first. I didn't do it earlier. And I'm going to import it as PG. That's a common convention to use this nickname PG for Pingouin. And then I'm going to import a data set which has a repeated measures variable within it. It's one I used in a previous example. It's a long, thin formatted data set where we have basically electrodermal activity arousal for 3 groups or for 3 levels of a polygraph lie detector test. So participants were asked a series of questions. They lied to some of them, they told the truth to some of them, they took part in a control task where they looked at like a neutral stimulus, and their EDA, electrodermal activity arousal, was recorded. So this is the data frame. Questions underscore LT col. It's got 3 group here, 1, 2, and 3. Lie, truth, colored squares. Arousal is our EDA, our representative measure of arousal. And we're going to conduct because this is the same participants in all 3 conditions, we're going to conduct Mauchly's test using Pingouin and the pg.sphericity method. So I'm calling Pingouin pg.sphericity, and there are a couple of parameters that I need to specify to run this test. Firstly, the data we're going to use is this df underscore EDA data frame that shows that I've just imported. I'm going to specify the DV. We know our DV is arousal, which is a representative measure of autonomics, electrodermal activity arousal. Subject equals person ID. So it's a repeated measures design, so we have to specify where the structure is, and we're going to use the person ID. So each participant has an ID number, and that by passing that in, it'll identify which data points are contributed by which participant. And then we're going to pass in our within subjects independent variable, which is our questions variable. So let me run that. And what you see is you get this quite interesting output. And it tells us sphericity results. It says sphericity is false for a start, so it's telling us we can't assume sphericity. That's kind of quite a nice little bit about the output there. It's telling us we can't assume sphericity, and it gives us this Mauchly's test of sphericity returns this kind of like capital omega, capital W, Greek letter omega test statistic, and it's 0.92 if you round it to 2 decimal places, and it returns like a chi-square value as well, and in this case it's 6.70 if we round that. It gives us the degrees of freedom for the chi-square and a p-value of 0.03. So you can see now why sphericity it's false that we've met the assumption of sphericity, because we have, if we round that to 2, that's 0.04. We have a statistically significant Mauchly's test with a p-value of equal to 0.04. It indicates we can't assume sphericity. We've violated that assumption. So like the Levene's test, as a test of assumption, the null hypothesis for Mauchly's is that the difference scores across categories are the same. As such, a significant Mauchly's test means we can't assume this and probably need to conduct some type of robust statistical analysis to test our research hypothesis rather than just run a standard ANOVA. Okay, so you can see above the Mauchly's test returns that. It returns this omega value, a chi-square value, degrees of freedom, the p-value, and our Boolean kind of true-false, indicating in this case that it's false. There are a number of ways I've seen Mauchly's tests reported. I'm not really fussy about it, but a common way is to report the chi-square value with chi-square value with the degrees of freedom in brackets and the p-value. You could also report the Mauchly's omega, the W as well. I've kind of seen that done as well. So, you could formally report it like I've done here. You could specify Mauchly's omega chi-square 2 degrees of freedom equals 6.70, comma p equals 0.04. I don't think it's wrong to report this value as well as the chi-square value. Okay, last thing I'm going to cover, as I mentioned, is tests of normality, and the Shapiro-Wilk test of normality was the one I mentioned at the start. And it's basically a statistical test, nice and convenient, that we use to test the normality of a variable's distribution. So if you've watched some of the earlier videos that I recorded in relation to this stuff, you'll know that my preference is to actually plot the distribution of variables and see what they look like, and then look at what your options are. But the statistical tests such as Shapiro-Wilk are available, and I'm going to conduct a test, a Shapiro-Wilk test from an independent group's design. So we're going to use that puppies data set that I used earlier in this video to check for normality at each level of a repeated measures factor. All right, so I'm going to test for normality using pingouin. So there's a pg.normality method, and that conducts a Shapiro-Wilk test. If I run that, what I'm specifying is I'm calling pg.normality. And I'm passing our happiness variable. Yeah, so what that's going to do is, remember the happiness is a scale variable. What's that going to do? What that's going to do is look at variances around the 3 groups of the categorical variable contained within the data, and we get this quite nice pandas table of values for a Shapiro-Wilk test. That's also like a capital W omega, and it is the test statistic for Shapiro-Wilk. So we've run it on our happiness. We've run it on our happiness variable. It's effectively testing for normality, and it's returned a Shapiro-Wilk value or statistic of 0.95, a p-value of 0.58, and a kind of Boolean value stating whether the variable's distribution can be classed as normal, true, or deviating from normal, false. So in this case, it's true. We've obviously got a non-significant p-value, 0.58, and as a test of assumption, the null hypothesis for the test is that the distribution is normal. And a significant result would indicate deviation from normality. So as I said previously, with the other two tests as well, if we get a significant result, it means we're finding a significant difference. The null hypothesis is that there isn't a difference for the Shapiro-Wilk and for the Levenes and the sphericity. And for this one, the assumption is that the data is normally distributed on our happiness variable. So a significant result would indicate that the data deviate from normality. It's true that we can assume it's normal in this case because it hasn't deviated from normality. Or the data doesn't deviate excessively from a normal distribution, and we're probably safe to use this variable for a kind of parametric ANOVA model. And we'd form the report this quite simply as we'd probably say Shapiro-Wilk test for normality was non-significant, and then just in parentheses report W equals 0.95, comma P equals 0.58. Okay, so that was the independent groups design. And for happiness, so we basically just we looked at the distribution of scores on the happiness variable. We can do a similar sort of thing for a repeated measures design, but note that here we need to include the data, the DV, and the categorical or grouping variable, okay, as parameters. So I'm doing a similar thing here, but whereas here we just specified the variable for our independent groups design. We called pingouin normality method to test for normality. Here we're specifying the data we want. We're saying which DV it is, arousal, which is the grouping variable. Okay, so it's the EDA. I'm using this polygraph data set for repeated measures design again. If we run that, what we get this time is more than one Shapiro-Wilk test. We get one for each level, as I said just up there. Each level of repeated measures factor on our repeated measures design. So I've done it. So what we've got here is Shapiro-Wilk for the independent groups, Shapiro-Wilk for the repeated measures, and it gives us more. It runs 3 tests essentially, and what we're seeing here is in all 3 cases we got a Shapiro-Wilk Amiga not but for group 1, which I think is lie, 0.98, group 2 truth 0.98, group 3 equals square 0.98. P-values are all well above 0.05, 0.68, 0.44, 0.41, and can we assume it's normal? True is what it states for our Boolean value. So, say in this case again, similar to when we just looked for the scale variable for the independent groups design, it's safe to assume that the data is distributed normally for each of the levels of the repeated measures design on our arousal or DV essentially. It doesn't deviate from normality because we've got these 3 non-significant p-values. So again, this one it would be safe to use this, or we can make the assumption that it's safe to use this in a repeat measures ANOVA design. Okay, so that was an extremely long video, longer than I intended, but quite a bit to cover. Hopefully that's useful. what we've covered here is there are a number of tests of assumptions that are quite commonly used before fitting or running some sort of ANOVA type model. For independent groups designs, we want to test for homogeneity variance. For repeat measures designs, we want to test for sphericity, and we might also want to test for normality, and we do that for both repeated measures and independent groups designs. Levene's test was used for the independent groups design. Mauchly's test for the repeat measures sphericity test, and we used Shapiro-Wilk, the pingouin PG.normality method to conduct Shapiro-Wilk tests for both the independent groups dataset and the repeat measures dataset. As I said at the beginning, there are a number of issues with this type of running these types of tests of assumptions. There can be a quick and convenient way to assess whether your data is appropriate for this type of analysis, so can be worth doing as a way to check. Okay, thanks for listening.